I'd like to especially thank the speakers, both Pierre and Aaron that came before me, because I think they did some heavy lifting. I hope that sitting through that hour or so of content, most of you are convinced that there's at least some role of AI and machine learning in doing this type of work. So certainly I'll cover a little bit of that, but more so what I want to focus on is sort of the practical nuts and bolts. So if you have an idea and you see that in the literature, it seems like it's something that can be solved, what's the next step, right? How do I actually go and start a project and build some of these tools, right? Is it true that I need, tens of millions of dollars worth of hardware? Is it hopeless for me if I don't have all the infrastructure built? And so I want to try to offer some of our experiences. Now let's see here, clicker, here, perfect, okay. So I want to just start here. Now, I'll go over some of the practical aspects throughout this talk, but if you remember nothing else, I would say the answer to that problem of how to get started can be remembered very succinctly with the fact that we do have a new center here at UCI with a vision essentially to provide the infrastructure and tools for all researchers on campus to actually get started in deep learning, machine learning type of projects. Now, if you haven't heard of us, that's not entirely a surprise. We've only been around for 6 months, so we're brand new. But that's part of the reason I'm here is to really give you guys a little bit of vision and a little bit of background as to what we can offer. And I will say that this extends not just within the UCI family here. Certainly, we have many projects with collaborators here, but outside of the Irvine healthcare system across California and across the country, we have dozens of collaborators. So this invitation really extends to anyone out here in this room. Now, in terms of the way that we've sort of developed and built this center, one of the key foundational principles is this idea of collaboration, right? So the bottom line is that there's almost an unlimited number of problems that can be solved with deep learning, machine learning applications. And certainly while we have some of those problems and a good understanding, especially me as a radiologist, I certainly don't have the domain expertise of the rest of you in this room who are vision experts, who are ophthalmologists. And so the way that we're able to turn around and build 20 or 30 different 40 applications is by relying on you guys to come up with the questions, right? And to come up with the data sets and to help us annotate and help us inject some of that domain expertise into the algorithm building process. It's actually a part of the development process that I personally feel is extraordinarily important. This idea of black boxes and machine learning algorithms that are completely trained without any human supervision, right? There's certainly some value there. But I'll touch upon this again at the end. I think it's absolutely critical that we build some of that domain expertise into the algorithms and really kind of blend the two types of approaches effectively. Now, again, I'm a radiologist, so many of these tools that I will show are radiology-based, but the same principles, as you've heard throughout the morning, apply broadly to many different types of applications, including ophthalmology and the types of diagnostic tools you use. All right, so thank you very much. Just before I continue, I want to highlight again this idea of translation, right? So our vision really is not only to build tools, but to actually try to use the tools in the hospital. Here's an application that actually sends every head CT in the ER to an inference engine to look for brain bleeds. In real time, you'll see that a new patient that's scanned in the emergency room is immediately interrogated by our AI system. And in the case of a positive hemorrhage, that notification is available to me as a user right away. Through the same interface, I can actually open up the raw images and scroll through the stack. And indeed, there is a bleed in the brainstem. And similarly, with another click, you can actually have the AI system identify the location of the hemorrhage and tell you the volume. So again, I know the theme today is essentially bench to bedside. So this is a very important part of what we do. We don't want to just show a proof of concept tool and publish. We actually want to try to use these tools clinically. All right, so how do we get to somewhere like that? Well, I think the first thing that you might take away from the talks earlier this morning is that if I have a data set and a project idea, I should just hire a programmer and voila, I've got an algorithm that works, right? It sounds very, very simple, but in fact what happens is that if you set off on performing your first experiment and designing your first project, you'll encounter a number of infrastructure-related problems that you don't necessarily anticipate starting out. So unlike traditional types of projects where you might look at 20 or 30 patients in a small cohort, we're looking at data sets now that are thousands, if not tens of thousands of patients, and the very simple task of storing that data or keeping it safe or annotating the data becomes exponentially more challenging. So these are the different steps, and we'll kind of talk about them. But the other point I want to emphasize here is that although building this infrastructure is extraordinarily challenging and takes a lot of time, once it's built properly, it can be shared by everybody, right? So if we have clean pipelines to get data, to anonymize data, and to create platforms for algorithm training, the rest of it is just sort of reusable in every downstream step. So that's sort of what our center provides. This is what we want to build and make available to the community here. And so let's go ahead and go forward. So the first thing, of course, as you'll see when you design one of these projects, is that you need a lot of data. Now, Pierre mentioned, of course, importantly, that there are a lot of techniques to limit the amount of data that you need, and oftentimes you can get by with smaller data sets. But the reality is that most state-of-the-art algorithms are still extraordinarily data hungry. Right? These are a few of the kind of internal data sets we've curated already in the past few months. A lot of radiology data. In fact, we have a clean pipeline now to extract and use any data in our PACS archive, anything that's been digitized in the past decade, so over 0.5 petabyte worth of imaging data. And similar systems are being built for our EMR, so any patient that's in the Epic system or any of the legacy systems prior to Epic. And then a lot of imaging data warehouses outside of radiology, so pathology, we've worked very closely with. I think ophthalmology is certainly a key player here and something we're very interested in actively building towards. Of course, if you don't have a data set available internally, there are a lot of public data sets that have been released. These are some of the radiology ones, but there are actually, in fact, a few very large ophthalmology data sets in diabetic retinopathy and some OCT imaging that you can use to get started, just to get comfortable with the techniques and to explore some potential ideas that you have. The next step, after you've identified a problem and you've picked out the right data set and found your patients, right, is to actually go through and annotate this data in some way. Now, again, because of the scale of the problem, because you may have 10,000 or 50,000 images to annotate, you do have to be creative with the way you do this, right? If you have a unlimited army of medical students, maybe you can get by with just manually annotating everything that you see, but on a practical level, we have to sometimes be a little more creative. What we oftentimes do is use a combination of both weakly labeled data as well as a few strongly labeled examples as needed. In other words, we can take ground truth reports and apply natural language processing to give an approximate ground truth answer. That is used to essentially train the first round of our algorithms. It's actually okay if there's error in that initial annotation process. It turns out that deep learning and machine learning tools are extraordinarily good at cutting through noise. So as long as the general trend of the annotations is towards the underlying ground truth, the AI algorithm will typically be able to pick out that pattern. From there, you actually assume that the AI trained system may be more accurate than your annotation. So you look for the discrepancies between the reports, the NLP generated annotations, and the AI system. And that's where we spend the costly time of having humans and experts look at those images. And in this sort of iterative bootstrap fashion, you can quickly annotate very, very large data sets. Now, of course, for a lot of problems, it's useful not to just have global labels, but to pick out the abnormality, to either draw boxes or to highlight and circle the abnormality, as we've seen in many examples today. And for that system as well, we've developed another in-house tool, so a web-based application that's connected to our backend, so it's connected to every single one of the images that we have throughout all our databases. And through one system, multiple users across the campus, across the United States, really could log in securely and help us annotate the data efficiently. And so this iterative annotation part, again, is just highlighting the need for the annotation and the machine learning specialists to kind of work hand in hand, trying to come up with creative solutions to get the data annotated. Now, when it comes to building the actual architecture, you do need some specialized hardware. I will take a slightly alternative perspective of Aaron in the sense that having $10 million worth of machines is nice. I absolutely would not argue against it in any way if you have those resources. But the reality is you can actually get started with a relatively modest budget. So if you understand what parts of the machine need to be upgraded and just focus all your resources on those important key components, things like GPU cards and network bandwidth, then you can actually put together a very reasonable and cost-friendly solution. Our center, just starting out, we have 20 GPUs, all sort of this prosumer level card, which essentially maximizes the amount of return for dollar. And again, we put it together and hand-built the system for just over $50,000. I will say that certainly when you're starting out and you want to build tools and you want to work together, this system is available completely to any of our collaborators. We set up web-based accounts, get you into our system, and if you're comfortable using Jupyter notebooks or other sort of web interfaces to do your development in the cloud, we can set those up and provide those for you. And then the last component here is the portion where we actually try to build the tools and put them in clinical practice. A couple of the key things here, without going into too much technical detail, is the fact that you typically need to build a separate parallel infrastructure behind the hospital firewall. So our research servers essentially are a little bit less secure. We assume that everything, by the time it comes to us, has been anonymized and cleaned, and we take care of that. But when you're dealing with patient data and you're using a tool that will potentially host patient-sensitive information, that typically needs to be built behind a separate system that we do have. That system has specialized hardware to run these type of machine learning algorithms in real time. And again, without going into technical detail, we essentially have a big environment where multiple algorithms all sort of live. And once a study comes in that has the appropriate prerequisites, it's this type of study of this organ system with this modality, that will automatically trigger a particular AI system to come to life and run and provide those results back to the physician. From the output side, we have mostly web-based tools, but certainly text messages, pages, even a mobile app that we have in development. Those are all options to put out any of the tools that are built and essentially developed through collaborations. And then finally, I would be, of course, remiss if I were to sort of highlight the things that our center offers and of course, ignore people. So people are our most important, valuable resource, I would say, that we have. The team that we've put together, certainly finding deep learning, machine learning experts and putting them under one roof can be a very costly endeavor. So we actually took mostly entry-level software engineers, people with passion and desire to work in medicine, but maybe not a lot of AI background. And I simply worked with them for many months to sort of bring them up to speed. In addition to 9 full-time staff, we have many visiting scholars, graduate student researchers, and undergrad, as well as resident fellows, which essentially really are the heart and soul of what we do and allow us to execute on the many projects. I would say another very important part of our mission is education broadly. So not only outreach to undergrad and sort of grad school level students where this type of education is popular, but actually into the medical school and into the residency programs. This is a part of the curriculum that really doesn't exist yet currently, but we feel strongly will be a very valuable asset. Even if you don't do ML or AI research, we find that there's probably some basic level of competence that everyone coming through the medical system should be able to at least appreciate what's there. They should be able to look at a new paper that's published and sort of critically evaluate and understand what was done. Again, even if they're not the ones that are building these tools themselves. So we have a curriculum that I teach to the medical students, and then we try to host as many workshops and hackathons and things like that to really encourage discussion between computer scientists, between physicians, and experts to essentially work together and do some of this work. All right, so that was a big overview. Again, it highlights some of the things that you can think about, whether you're actually coming and working with us, or if you want to build a similar type of system at your own home institution. Those are probably the important parts to consider. Now, the speakers before me already did a fantastic job of highlighting what AI can do, so I won't belabor this part of it too long, but certainly I'll show some examples in radiology that might serve as sort of inspiration as you come up with your own ideas. So what kind of things can we do in radiology? Well, I would say one of the most popular and easy things to tackle is trying to find some abnormality, to do simple detection and localization of an abnormality and bring that pathology to the attention of a radiologist. This here is a tool to look for a clot in patients with stroke. This particular type of clot in a very specific distribution can be treated immediately with surgery. So rapid identification here is very valuable. Similarly, you can detect cancers of multiple types, either on regular X-ray imaging or MRI, and hemorrhage. So that hemorrhage tool that you saw initially, typically these are not findings that are very subtle or difficult for a trained expert to identify, but clinically provide value because by automating that process, you're introducing new paradigms that would really otherwise be very difficult to manage. For example, if I come in on a weekend in the ER, I may have 30 or 40 patients waiting to have their images read. A finding like this is not hard for me to see, but still might take me 1 or 2 hours by the time I come to that patient. A tool that immediately identifies positive findings and alerts me to read that image first, again, has a lot of clinical value. In addition to identifying and detecting abnormalities, the fact that we can quantify an abnormality is very valuable, as we saw in multiple examples again previously. Here we're quantifying the amounts of hemorrhage. The same can be said to quantify and estimate the volume of various tumors across the body. Here's an example with kidney cancer. In addition to quantifying volume, another thing that the AI systems are very adept at doing is essentially quantifying or objectively trying to evaluate some finding on a continuum. This is an example in prostate cancer where humans try to assess the prostate cancer along several dimensions and assign a specific PIRAD score based on the amount of darkness or the blurriness of edges. This is something that AI systems can do very well. It's a very objective problem. I just simply need to put it along a continuum. And we've shown that not only does the algorithm perform well, it actually does so in a much more reproducible and reliable fashion. Of course, these examples extend far beyond just radiology images. Here's an example of looking at manometry tracings, so pressure tracings along the course of the esophagus over time. The images are slightly different, the problem is slightly different, but fundamentally we have some sort of diagnostic data, whether it's time series, whether it's image, and we're trying to map that particular data to a diagnosis. The same has been done, of course, and also shown a few times today in pathology. So in this particular example, 2 examples. One, we have a tool that goes through and identifies various Alzheimer plaque morphologies. Another tool here on the left with the pink H&E images is a tool for counting cells. Again, not a particularly challenging task for a trained pathologist, but the fact that you automate it means that I can now run this analysis over an entire digitized slide. Right? So not only look at high-powered fields and tell us what they see, but project that finding across an entire sample, and now we have a type of data, a type of output that would otherwise be previously impossible and potentially yield other interesting diagnostic data. And finally, of course, as we've seen many times today, the use of optical coherence tomography and other tools where you're essentially scanning through a very small structure. You have at the output a very, very large data set that may be tedious or difficult for a human to go through in high detail. This is certainly something that various AI algorithms and architectures can solve very, very effectively. All right, and this is my last example. So again, I think Pierre flashed the slide earlier as well, but this last category of tools now falls into the question of whether AI or machine learning tools can teach us as humans something. So typically it's humans coming up with a label and saying, AI system, please learn this mapping that I've told you. But can the reverse also happen? And in fact, it can. So this is a tool where in the first phase, we trained an algorithm to go through brain MRIs and identify brain tumors as well as their underlying molecular mutation. So just based on imaging, predict what mutations the tumor is. And so that's a classic machine learning problem, very simple to solve. But after we trained the algorithm, we asked, is there a way for the algorithm to tell us what it learned? When you tell me it's IDH wild type or a 1p19q codeletion, what is it that triggered that that diagnosis? And in fact, that's what we did. The algorithm can't talk to us in English. It can't communicate, but it can show me prototypical examples. So we went back, reverse engineered the features and said, what are the most common or the most prototypical examples of each of these mutations? And on its own, the algorithm is able to generate what turns out to be an atlas of common findings. And what was interesting here was that if you look through the literature, you'll see case examples of single or two experts coming up and saying, after my 30 years of reading brain tumors, I suspect that this is probably a pattern that's come up in the past, right? But typically these are just one-off patterns here and there. If you go back and accumulate all of that literature and do a thorough review, you'll find that it essentially comes out to these patterns that the AI system recognized. So in fact, something that's very powerful and interesting. So with that, I do want to open the floor for questions. Before I do, I think the comments and questions that came up in the past two sessions, one thing I noticed was this idea of explainable AI, black boxes, and when these tools will be ready for prime time clinical use. And I'll give you my answer there. I think that AI tools will be ready once we're confident that they can essentially replicate what humans do, and importantly, never make an error that humans would make. So in other words, with the way a lot of black box systems are designed, even though it predicts with 98, 99% accuracy, it is possible that a single adversarial sticker or some little part of the image that's noise can completely drive the algorithm to make a very unexpected prediction, right? And so what that might mean is that a patient with a very large hemorrhage or a very large stroke randomly gets misclassified as the wrong thing. I would argue that that's an unforgivable mistake, something that if you ask 10 radiologists, all 10 would agree is egregious, right? By contrast, if you inject a little bit of domain knowledge and expertise into your algorithms, I think the idea of encapsulation that Pierre brought up is absolutely on point. So dividing the task up and creating endpoints that I as a human can now interact with and understand, then the algorithm will only make mistakes that humans would also probably realistically make. So maybe it looks at an area of artifact and high density caused by hardware and says, I think there might be a small hemorrhage there. And I'm an expert and I'll look at it and say, yeah, you know what, I think it's fine, but I understand why you made that mistake. You know, it was high density. That's kind of what blood looks like. If you can ensure and design a system to map to those type of findings, to tell you what it sees and think the way a human thinks, then I think the tools will be much more ready for prime time. I think currently the fact that you can very easily trick an algorithm and you can occasionally find mistakes that don't make any sense, I think that's what we need to avoid before these tools can be used. All right, so with that, I'd like to thank you guys for your attention and open up the floor. I would say we're discussing a lot of projects, but right now I think the missing part is the infrastructure. So I know at University of Washington, what Aaron just showed, I think that's an amazing kind of infrastructure and system to have built. I would say in many ways we should move towards building something similar. I know there's a lot of the ophthalmology imaging databases are built in a similar way to our PACS system. So there's IPACs and things like that. There's no reason that we can't be building parallel structures here in the Department of Ophthalmology. So I would say, this is my contact information, and please reach out and let's try to build some of these types of things together. Right. So I would say that that is a byproduct of the fact that the low-hanging fruit tend to come from images and things like that. But that's not an inherent limitation to the technology at all in any way. Number one, I would say one of the biggest opportunities right now is trying to combine imaging data, which is readily accessible, and integrate it with non-imaging demographic sort of background data. It turns out that for machine learning tools, it could be tricky, but deep learning specifically makes it very easy. So we can integrate patient treatment histories, backgrounds, and things like that. As for prediction, I would say, again, there's nothing inherently challenging about that prediction problem if you have the right data. In radiology, we had a big landmark paper recently where on PET imaging, we were able to show that deep learning systems can predict the onset of Alzheimer's disease up to 7 years before the patient showed symptoms. That happened again to come from imaging, but that's not a limitation. It is something that's very feasible. If there's a signal, if there's something there that essentially will lead to a downstream diagnosis, if that pattern exists, it's something that we can uncover. So actually, Bill is, I believe, the next speaker, and he'll actually do some really nice demos similar to Pierre did, where inference from an AI system can happen so fast that it can be performed real time with video frames, right? So again, when you train a network, it's very extraordinarily time consuming. And when you're building the network, that initial architecture may be very large. But when it comes to inference, there's many creative things we can do to speed up the process, right? One is that you can compress models. Most of the weights that your model learns from has been proven to not really add that much incremental benefit. So you can just prune the neurons away and leave a very lightweight model to be used. And again, the actual hardware to drive it, compared to training where you might need many GPUs and lots of compute power, the inference is very fast and very efficient. So in real-time prediction, you may need a GPU, but oftentimes for something like hemorrhage, you don't even need a GPU. You could run it on a CPU and have really no significant degradation in performance.